Voice of the Sea, learning from experts across the ocean. Welcome to Voice of the Sea. In this episode, we're at the Gump Research Station on the island of Moorea in French Polynesia, learning about how climate change is affecting corals and changing the world with Dr. Ruth Gates. Corals form the backbone of reef ecosystems, providing structure, habitat, and food for the other organisms that live on the reef. Ruth has studied corals from Hawaii to the Caribbean, Australia, the Philippines, and Tahiti. Ruth's work is aimed at helping corals survive and recover from climate change, natural disasters, and other ecological threats.
Here in Moorea, we tend to come down once a year, and the work that we do is part of the long-term ecological research that's going on here on reefs. But in Hawaii, we have some of the similar species that we have here in Moorea, and we're very interested in looking at how they function here in Moorea as compared to Hawaii. So we have a big comparative program where we'll look at exactly the same things, but in these two very different locations.
At the same species of coral, but living in two different communities.
Locations, exactly. And it's really interesting because reefs are actually very different all over the world. The party line is, say, that all coral reefs will be dead by 2050. That is just not true. Reefs in Hawaii are very different to reefs in Moorea, and those are very different to reefs in the Caribbean or in Australia. So in Australia, there are hundreds of different species of coral, whereas in Hawaii, there's under 50. These are very different types of places for corals to live. So I think this idea that you can really sort of bin them into one corals is actually a little bit too blunt to really understand how they function. These labs are amazing resources. The other thing that's wonderful about working in a lab like this is you would generally only see people in education programs coming down here and working on the reef itself. What's wonderful about having labs like this is that we can take students out onto the reef, we can point out problems on the reef, like perhaps corals are bleaching, or we're looking at diseases, and then we can take samples of those corals straight into the lab and we can start to analyze them, and we can show the students why there might be differences. We can introduce them to techniques that they would think wouldn't be found or wouldn't necessarily be applied to the setting that we're working in. Forensics, DNA analysis. These are things that people think are CSI, right? That this is not really what we do in the marine setting. But the reality is we apply all of the tools of modern medicine to evaluate the health state of our marine resources. The process of biology is you think of a question, you frame it like a hypothesis, you test it, and when you get the data back, you let the data decide whether or not you accept the hypothesis or answer your question positively and negatively. Quite a lot of the time, I might be stupid, but quite a lot of the time, we end up not getting the answer that we anticipated or rejecting our hypothesis. But we definitely uncover or unveil aspects of the biology that we've never even considered before. And so this is why biology is such an amazing subject, because it's all about discovery. People talk about that when they go to space, that it's space discovery, it's all up there, it's uncovering new things. Well, every single time I go in the water, I uncover something new that I didn't know. And then when I go and do research about it, I realize actually nobody knew. And so then I report that finding to obviously my colleagues, but also I try to introduce a broader audience to those findings. Now you can use, of course, all the social media and websites, and you really have opportunities to extend the reach of your science now that we never did when we were training. I am absolutely driven to understand why corals function in the way they do and how sensitive they are to change. And there are many changes going on in the marine setting. So we have the pressures of climate change, that is gradually warming waters and waters that are becoming more acidic. That for corals is extremely problematic because they require the water to be in a particular chemistry range to be able to deposit their skeletons. And of course, it's the skeletons that create the structure, that house the fish, that feed us and protect our landmass. So I'm very interested in understanding what is the range in which corals can function, and also understanding why some corals are able to function better than others. And I want to understand that, Kinesia, because if we can understand that and we can harness that knowledge, we can potentially then breed corals to be better able to withstand the future. The goal is to sustain our ecosystems, and this idea that all corals will die is a gloom and doom scenario that is very difficult to really even begin to act around. And I believe there's things in the biology of corals that really account for why they've been on the planet for millions of years. And I think we are changing the environment very rapidly at the moment, but we are also in a time when technology and new approaches are emerging in parallel. And my research program is really interested in harnessing fundamental aspects of the biology and forwarding an agenda of developing capacity to adapt to climate change.
The University of Hawaii's Sea Grant College program focused on Hawaii's coasts and its communities through sustainable development, safe seafood supply, sustainable coastal tourism, hazard resilience, and healthy coastal ecosystems. Hawaii's Sea Grant.
Cozy Island Earth, bringing together university, government, research, and community partners to improve science education and ocean stewardship in Hawaii.
You're watching Voice of the Sea. We're back in French Polynesia with Dr. Ruth Gates, learning about coral reef ecosystems, how they are unique, and how they are uniquely threatened by the effects of climate change and ocean acidification.
Moorea is one of the most dynamic reef systems I've ever seen.
Why?
Because it has been hit sequentially by damages that are extremely profound. And what I mean by that is, I think when I first came here in 2004, it was about 70 to 80% live coral cover on the fore reef. And there was a massive storm that came through and wiped the reef clean, essentially. It was like a lawnmower had gone across it and just wiped everything out. And that's happened again so it's happened twice now since I've been coming. And
since 2004.
I think since 2004, with the major damage. There was another really major damage last year with the Crown of Thorns outbreak followed by another big storm. And what's stunning about this reef is it is obviously connected to a huge reservoir of new coral propagules. Baby corals are coming from somewhere. And so when it was wiped clean, within a year you could see what we call the popcorn stage, where the whole fore reef is covered with popcorn corals. They're all the same size, tiny little 1-year-olds, and those things are now growing up and the reef is now creating its structure. And you wouldn't think that it could recover this quickly, because we all think that reefs, once you lose a lot of reef, that it just doesn't have that resilience. And this is what we mean about resilience, the capacity to be hit and to bounce back, essentially. And here, there's something so fabulous about the way the connections work. We don't really fully understand where all of the juvenile corals are coming from, or why this particular reef system has the ability to bounce back like this, but it is. And it's a remarkable situation. But it sort of highlights how important it is, the discussion of coral reproduction and maintaining corals in good enough health such that they still reproduce. Because if it was not for this sort of stimulation of the reefs with new corals coming in from somewhere else, this reef would be dead. And it would remain dead. So the implications for climate change on coral reproduction, if there is a tipping point, it is going to be in reproduction, and reproductive failure will, coupled with a big disturbance like the one that's happened here in Moorea, will have dire outcomes. We have a massive population. In fact, many of the things that are happening in our world is to do with the very size and growth of our population. We have to feed. And it's always at the expense somehow of our natural environment, either in terms of urban building and developing large pieces of land to house people, or growing lots of plants that can be basically grown, or livestock that can be grown en masse for food. But it's always at the expense of the natural setting. And as somebody who's a conservationist, I'm very aware of the tension and the need to feed the population and to house the population. But I'm an optimist, and I believe it can be done in a way that is respectful to the environment and sustains those resources. Because our reefs, for example, are so important to us as humans, and yet that part of the conversation doesn't necessarily get aired that clearly. Many people don't know that corals are living animals. So if you step on them or you ram your boat into them, it's going to kill them. And many people don't know it's that living animal that creates the structure where your food fish live.
Right.
And that's what's going to sustain you over time. So coral reefs are critical for food security. But the other thing I think that we underestimate is how important it is to our well-being to be in beautiful places. That sense of you come to a place like Moorea and you are overwhelmed with the sheer stunning beauty of it. And when you go in the water, you have that same experience as you look on the reef. It's an underwater garden full of colors, and somehow that feeds your soul. And we don't talk much about that. And but in my opinion, it's that balance. It's that balance of trying to maintain your resources against the backdrop of the need to really accommodate this ever-growing population.
In your work, you talked about reef restoration. What does that mean?
Well, so unfortunately, I wish there wasn't a need to restore, because really what that means is there's been a severe damage that has taken a large number of living corals and essentially leveled it. And that can happen under circumstances where we have, say, development, where land is cleared above a reef, and then there's a massive rainstorm that coincides with that clearing, and all of the topsoil essentially piles into the marine setting and buries the reef. Over time, that sediment will get washed away, but the reef is gone. The reef is damaged beyond repair. And so in those cases, there's a need to essentially restore, and that can be done by replanting corals. It's done all over the world, actually. There's been many places, particularly in Asia, Thailand, Indonesia, where there are very large farms where corals are being divided and grown as tiny little corals on strings, and then when they get to a certain age, they then can be transplanted onto a reef.
Wow.
And they can recreate. Now, that is a wonderful effort, and it's something that I'm very supportive of. What we bring is a little bit more understanding of what are the implications of taking, say, an animal, and because corals can reproduce clonally, that means essentially you can split them in half and you have two identical individuals. And you can do that again and again and again, and you can get to a situation where you have hundreds of replicates of the same individual, and they all grow independently. So you could essentially take one coral and have 100. So you would think that would be beneficial. But if that particular individual is a very sensitive individual to stress, all of those individuals will actually respond similarly to the stress because they're all identical. And so one disturbance can wipe that entire 100 corals out. What we're attempting to do is to suggest that we partner, so we not only reproduce clonally, but we introduce sexual replication into the system. So we would take perhaps one of individual A and we would breed it with individual B. So now we're mixing the genetics, and then we're creating a slightly different genetic individual, and it's that genetic variation that is the framing for one being able to withstand stress better than the other. And we're particularly picking those members of the population that are the best at withstanding stress. So the super athletes among us. We're selecting them, and we do that selection using a series of experiments. And we do many of those experiments down here in the aquarium setup.
In addition to building super corals in the lab, Ruth is researching how increasing levels of carbon dioxide in the ocean are lowering pH, making the ocean more acidic.
The changes in pH aren't easy to visualize. You say, well, we've had demonstrations of people putting pieces of chalk into a vat of acid, and it starts to froth and dissolve, which is essentially what will happen if we go very, very acidic, right? But if you do the same thing with a coral skeleton, it actually doesn't do that, because they're very subtle changes. So we don't think that ocean acidification is going to dissolve corals.
But it keeps things from forming.
That's exactly right. So it's just essentially interfering with the mechanisms by which they lay new calcium carbonate or skeleton down. So they're slower, and eventually they come to a stop. And because there's constantly a loss in the system anyway, so some skeleton is lost at the same time as some skeleton is put down, that you have to keep that balance positive to grow. But as soon as that equilibrium point changes, that balance shifts, then you've got problems. It's not going to be dramatic, and you won't expect to go out and see a fizzy reef, right? That's not what it's going to look like. But it's these, what we call chronic and more subtle effects. We also study quite a lot how these types of disturbances are influencing what is perhaps the most fundamentally important process on the reef, which is coral reproduction. So in order to be able to keep going, you have to generate new individuals to put into the community, because there's always life and death in any species. Some of the more subtle impacts of these stressors is that corals maybe aren't reproducing as well. They're not putting energy into creating new life because they're so busy trying to keep growing and trying to lay down calcium carbonate. That's where they put all of their energy. You know, people will often say, you'll either grow or you'll reproduce. You know, let's face it, we don't generally reproduce when we are growing as humans. We are pretty full grown by the time we put our effort into reproduction. And so that's the same with most individuals. So if there's a struggle to grow, the thing that's struggling to grow will probably not reproduce. And that's a sort of an effect that isn't that obvious when you look at corals, because corals do this bizarre thing of reproducing only on particular nights of the year in the summer months. They do this mass spawning thing where they put all their effort into producing eggs and sperm or larvae and then releasing them all at once, which is crazy to watch, and the coral spawning events are something to behold. But you know, there's a general feeling that they maybe aren't quite as profound as they used to be, that there's less eggs and sperm going out, that fewer colonies are maybe reproducing. And then that over time has really serious implications for how populations anywhere in the world will respond to climate change. And so there's a big move to start to cryopreserve or freeze coral eggs and sperm.
Oh, wow.
And there is for many, many, many species that are considered to be sentinels of change. So corals, because of the way that they seem to be extremely vulnerable to temperature disturbances. They live close to the thermal maximum already, the threshold that they start to die at. And so they call them sort of the canary in the coal mine, because they are the indicator that something is going horribly wrong in the marine system. And you know, whether that's true or whether it's just because we look at them a lot and we can see those changes, and those changes are very obvious, it doesn't really matter. We know that change is happening. We know it's happening at a rate that has never happened before. And we know that links to changes in temperature and to ocean acidification. So the idea that we may need to protect the resource by biobanking, that is, protecting eggs and sperm, keeping them artificially producing juvenile corals, that is already part of the discussion. And it's a part of the discussion that not many people know about. But these are alternatives. These are ways forward. If we push our ecosystems too far, we can intervene. And we've done a lot of this with human reproduction, right, where you know we freeze embryos all the time, and we implant all the time. And so we accept that kind of an intervention for humans. But we're talking about these kinds of interventions for natural systems. There's still quite a lot of discussion to have, I think.
Exploring Our Fluid Earth is the dynamic curriculum developed by the University of Hawaii's Curriculum Research and Development Group. The award-winning Fluid Earth and Living Ocean textbooks are now interactive and online. New activities, updated content, and a teacher community. Exploring Our Fluid Earth is now freely available. Find out more at exploringourfluidearth.org. Welcome back. We're with Dr. Ruth Gates, Director of the University of Hawaii Institute of Marine Biology, talking about how her research, knowledge, and excitement continues to grow.
I've been working on reefs for 25 years, and I think you start thinking, you just want it to be stable, you don't want anything to change, but what I realize is everything is changing constantly. Reefs are really dynamic places. The same, we don't actually even know how long a coral naturally lives on a reef. We call them everlasting because they can be everlasting. They can be 600 years old, but actually the majority, I think, turn over much more quickly than that. And I think the technology now allows you to really ask those questions. Very long-term time-lapse photography allows you to study the same coral over time. Continual photography of individuals over very large spaces gives us an indication of how dynamically turning over these systems are. But it's really exciting times for coral biology. It's always going to be exciting times for coral biology as far as I'm concerned, because they're fascinating. Yes, there are some corals that are surviving, but there are many that are not. And the number that are not is probably increasing as climate change pressures collide with local impacts. There are only very few reefs in the world that have been studied. And there are many reefs that have hardly been visited. And so it's very hard to sort of accept the idea that we're going to just assume that we know that these reefs over here that we've never even looked at actually function in the same way as this reef over here, because somebody who's worked on reefs across the globe, no two reefs are the same. And what I know about Caribbean reefs has almost no value in a Pacific reef. And the first time I went to the Great Barrier Reef, I got in the water and I dropped my regulator because I couldn't get my head around how many corals there were. It was a completely different setting. It was like a completely different garden. It was like going from an English garden to a completely manicured French garden, or vice versa probably, because that's how we do it in England. But it was just completely different context, and what I knew was just not valuable in that context. So I had to do a lot of learning very quickly, and that's what we do every day as scientists, right? We just learn every day, and we hope we know something.
Thanks for watching Voice of the Sea.
The Curriculum Research and Development Group in the College of Education at the University of Hawaii at Manoa. CRDG's training roots go back over 40 years. Through professional development programs, curriculum workshops, research on teaching methodology, individualized school and district training, and so much more. The Curriculum Research and Development Group, improving schools, improving education. CRDG.
Turn your love of the ocean into a lifelong career. Join NOAA, the National Oceanic and Atmospheric Administration, as we unlock the secrets in the deep oceans, track rapidly moving storms, model climate trends, protect and preserve our marine resources, and so much more. It's all in a day's work at NOAA. Find a career that makes a world of difference, enriching life through science, service, and stewardship. NOAA.
Kosi Island Earth is working to establish new avenues for connecting research scientists with educators and communities. Kosi Island Earth is working to enhance the science and ocean literacy of our island residents and visitors. Kosi Island Earth is working to connect scientific research, traditional knowledge, and ocean policy. Kosi Island Earth, bringing together university, government, research, and community partners to enhance ocean literacy and engage all ocean users in stewardship.